Hello, I will be presenting our research topic, measuring the quality of medical notes. On the team, we have Matthew Raporte, Vladislava Pastova, and myself, Zachary Volker. Clinical notes are a crucial mechanism for doctors to communicate their observations and potential diagnoses between one another. When a patient transfers doctors or hospitals, it's important that these notes include detailed insights uncovered by the last doctor for them to see, so the following medical team can continue their treatment plan and understand the full context of the patient's medical history. A good analogy for this are README comments and code comments. Because of their complex, unstructured nature, there is very little research on evaluating the quality of these notes. But being able to identify doctors who write poorly and help workshop their skills would be very useful to hospitals, especially if this could be automated and standardized across hospitals. This system could also be used to reward/incentivize doctors who write high quality notes. Picture right. If such systems were widely adopted, the overall quality of electronic health records data would be improved, leading to quality improvements in healthcare treatments and lowered costs through automation. So we will first delve into research that is currently out there covering about NLP, deep learning, and the usage of electronic health records. Deep learning has proved effective for many non-medical applications, such as named entity recognition, sequence labeling, sentence analysis, and language understanding. Shown here, we have a few papers discussing how deep learning has impacted NLP. NLP in itself has been a huge help to the medical community. However, for medical research, most teams manually build custom models and datasets to solve their problems due to the lack of data. With the increased interest in deep learning and open source data nowadays, deep learning, NLP, and medical research are all within reach of each other. One thing we've seen throughout all these papers is that there is a focus on predicting patient outcomes. We didn't see nor come across any research that dealt with measuring the quality of medical notes. Our paper will discuss how we could measure this quality and describe a few approaches for implementing these measurements. We had a few approaches that we initially came up with. Our cluster approach would use pre-trained embedding models to project notes into the latent space, notes being doctor's notes. We would create clusters from this data, then find the average distance and variance on a per doctor's basis to use as a metric for how effective a doctor can communicate. Intuition being that doctors talking about different diseases or topics should cluster together at some base linguistic level. If doctors spray from that cluster, it means they're not effectively communicating like other doctors. Issues arise with high dimensions with the curse of dimensionality, and there is a lack of an objective measurement. We also need domain experts to help us debug these clusters and see if clustering is right for this solution. We would also need help from domain experts here, especially with learning new tokens and seeing if these tokens are being correctly classified. It is also fairly easy for doctors to play a game with this and fix their problems instead of actually working on their communication skills. We don't want to encourage doctors just to fix their token recognition. We want them to work overall to better their communication skills. Our next approach deals with making models to take in doctor's notes and perform various tasks, i.e., predict mortality rates, prescriptions, length of ICU stays, etc. This intuition being that models will learn in general how doctors communicate to predict various outcomes. The models are now the interpreters of the doctor's notes, and we want to see how well a doctor performs in these models. The pipeline would be we train models with all the data, we group notes by doctors, we send notes through the model per doctor to see what kind of error we get back. The higher the error, the harder it was for the models to interpret the doctor's notes. Therefore, would be difficult for others to interpret their notes as well. There were issues with this approach as well, but it is one we ultimately focused on due to its objective measure and ease of adaptability and extendability. With all of this said, how do we standardize this text data? First, we have to understand it. First, note that doctor's notes and biogram counts have a long tail, and doctor's notes tend to be much longer than normal NLP tests, like 4,000 texts or 25,000 texts. Also, because of medical terminology, the grammar and words that are used in this dataset are not what you typically see in an average NLP dataset. So, asking the question again, how do we standardize? We first tried cleaning the data using SCAPI and NLTK for stemming and lemmatization. We were hoping that cleaning it up would make the data scale back a little bit, make it more easier for us to use making our own embedding model or using a pre-trained one. Results were not good, mostly because there was a lot of tokens in this data set that were not in normal data sets that needed a lot of information. Fortunately, we found a better approach. We have access to publicly available BERT embeddings that have already been trained off the Mimic 3 database. This paper was published a little over a year ago, and you can find more information from this paper. To handle the large number of sentences and high sentence counts variability, we created two datasets. One where the top 3 sentences were concatenated and encoded into one vector, and another where we encoded separately and created a short sequence. Due to the lack of time, we limited our scope to just these two methods. For our downstream models, we focused on a prescription model, where we would take the embedding of the last notes before the prescription was made and pass it through our model to see if we can correctly guess the prescription that was given. We will pass it through two models, CNNs and a variable length RNN. We do recognize that earlier notes are relevant as well in the decision-making process, but our models were not very effective at processing so much data. So, with our TF-IDF approach and our BERT approach, we can see that the TF-IDF approach gave us 3 to 4% accuracy, which we could look at a baseline. And then with our RNN, we saw it was a 5 to 6% accuracy, which was okay, but using our CNN really increased our accuracy up to 19 and 20%. However, these still aren't the results we were looking for. To get errors from them for doctors, the distributions were really crazy, and there was nothing really to gain out of it. In conclusion, dealing with medical data was strenuous. There seems to be no real standard about how doctors write notes and how doctors dole out prescriptions. Both of these caused friction and wasted time in our research, so if this work should continue, either there needs to be a standard in data cleaning and pre-processing methods available for people who do this kind of work, or there needs to be a standard for the doctors to write out notes and write out prescriptions so that way it can be easily parsed downstream. In any case, seeing the large performance jump between the TDIF approach and our CNN approach makes us hopeful that deep learning is the right step for working with NLP and medical electronic health records.